In this video, we're going to take a closer look at alkenes. Now, as you may remember from our previous video, alkenes are a class of hydrocarbon, meaning that they have carbons and hydrogens, but they have specifically carbon-carbon double bonds. Now, unlike alcohols, you might not immediately think of anything that you commonly encounter that contains alkenes. However, alkenes are actually very important, both biologically speaking, as well as in our synthetic applications. Alkenes are found in a variety of different plastics, like the polyethylene plastics. Those are composed of alkenes that are reacted together to make these very large plastic molecules. In our biological systems, we also have a lot of biological molecules that contain alkenes. Things like olive oil and those omega-3, omega-6 fatty acids that we hear about a lot when we talk about nutrition. So, in order to get a better understanding of those different molecules, we need to gain a better understanding of our alkene functional group. As with our other functional groups, we're going to look at our three different categories here. We're going to look at how we can name our alkene functional groups. We're going to look at the properties that our alkenes share. And we're going to look at their reactivity. So first, we'll start with naming. As usual, our alkenes will need to be named using a unique suffix. So for alkenes, we're going to use that -ene ending to indicate the presence of our alkene double bond. So again, if we have a 5-carbon molecule with a carbon-carbon double bond, making an alkene, we would take our usual prefix. So 5 carbons, that means our pent prefix. This is going to be pent. And then we use that -ene ending to indicate the double bond of our alkene. So our structure here becomes pentene. Now again, as we saw with our alcohols, we need a number to indicate where that double bond is. So we use that number to indicate the position of our functional group. As always, we want to count so that we give the lowest possible number to our functional group. So since our double bond is closer to the right side than the left side, we're going to want to start counting from the right side. Our first carbon and our second carbon, and of course here at our second carbon is where our double bond starts. Now of course our double bond goes between two carbons, goes between the second and the third carbon. However, we only just need to use the first number, our 2-pentene, to indicate that the double bond starts at the second carbon, and of course then it proceeds to our third carbon. So only one number is necessary. As with alcohols, we can also rearrange this, and we can say that this is pent-2-ene or 2-pentene. Both of these are appropriate names. Now, of course, the next thing we can consider is if we have multiple functional groups, such as our alcohol functional group and our alkene together. Now, as before, with our alkyl halides, our alcohol will take the higher priority. So what that means is that we're going to number our molecule in order to give the alcohol the lowest possible number, even if that gives a higher number overall to our alkene. So in this case, if we number from the left side, 1, 2, 3, 4, 5, 6. So our alcohol is at the 4th carbon. Now let's compare that to numbering from the right. 1, 2, 3, 4, 5, 6. So the alcohol is at the 3rd carbon from our orange numbering from the right side, and that will be the numbering system that we'll use to get our name. So at this point now we have 6 carbons that we counted out. So 6 gives us our hex prefix, and now we have to add both our OL suffix from the alcohol as well as the en suffix from our alkene. So we can do this like this. So we have hex, and now we're using the orange numbering. So this is hex 4-ene, and then we also put the alcohol in there as well, 3-ol. So it's hex 4-ene 3-ol. Or we could also write this as 4-hexene 3-ol. Both of these, again, are appropriate ways to represent our overall molecule name. Now, there's one final factor that we need to consider when we're naming our alkenes, and that concerns Alkenes Stereoisomers. So as we compare these two alkenes here, so initially we can see they should be very similar. They should have similar names. They both have 4 carbons, so they are bute. They use that bute prefix. And they both have that alkene in the middle. So this would be 2-butene. Right? That alkene double bond is at the second carbon for both of these alkenes. Now you might think, well, in order to get from one of my molecules to the other, I just have to rotate around my bond here and point this carbon down instead of up and to the right like it is here. However, we have to remember here that this double bond that we're seeing in our alkene is, of course, actually represented by this pi bonding system, where we have our 2 carbons. They're sharing one bond with their 2 sp2 orbitals overlapping. So they overlap head to head to make a sigma bond. And then the second bond of my double bond comes from these 2 p orbitals, and these actually overlap side to side to create a pi bond. Now, since these are overlapping side to side, if I were to rotate this, I would have to break that pi bond. So what that means is that my double bond can't really rotate. So double bonds don't rotate. If they were to rotate, they would have to break that pi bonding, which would cost a significant amount of energy. So under most conditions, these 2 different alkenes are unique molecules, right? We can't just rotate to convert in between these. So I'll put a little X over this arrow to indicate that I can't do that rotation here to convert between these 2 butene molecules. So I have these 2 molecules that are in fact unique molecules. Right? Again, they are diastereomers because although they have the same overall structures and connectivity of their atoms, they differ in terms of the spatial positioning of where my atoms are. Right? So my atoms are pointing up in relation to the rest of the molecule over here, whereas they're pointing down in relation to the rest of the molecule over here. So it's a new kind of stereoisomer. Another kind of diastereomer, similar to some of the diastereomers that we've looked at previously. And I'm going to need a new naming system to account for to differentiate between these 2 different alkenes. So we're going to use first the cis-trans naming system that we introduced with our cycloalkanes. So remember, cis referred to when you had 2 groups that were pointing in the same direction with respect to the ring. Trans refers to when they're pointing in opposite directions with respect to the ring. So we can use the same nomenclature here. In this case, I have my double bond, and I have one bond pointing out in this direction, and one bond pointing out in the opposite direction. So I can refer to this as trans. So this is going to be my trans 2-butene diastereomer. And down here, both of these bonds are kind of pointing in the same direction relative to my alkene. Obviously they have different angles here, but they're still both kind of pointing away from my double bond in the same direction. So I refer to this as cis to indicate that they're both pointing on the same side, similar to what we did with our cycloalkanes again. Now with our alkenes, there's also another nomenclature system that we use for our alkene diastereomers. So this is a E and Z nomenclature system. So our trans diastereomers we also call E. So this would be E2-butene. And our cis diastereomers we refer to as Z diastereomers. This E and Z come from German names actually for whether it's on different sides or the same side. One easy way to remember this is that you can think of Z as indicating that they're on the same side of the alkene double bond. Now for our previous examples, it was fairly easy to tell whether, again, our bonds are pointing in different directions to make a trans or E diastereomer, or whether they're pointing in the same direction to get that cis or Z diastereomer. However, if we have more complicated alkenes, such as the structure shown here, it becomes slightly more difficult to determine whether it's cis or trans. So in this case, we have our 4 bonds to carbons coming out on either side of our double bond. And we are going to have to rank the bonds according to priority, similar to when we're naming our enantiomers, in order to determine whether it's cis or trans. So first we'll kind of split it down the middle, and we're going to consider both sides of our alkene double bonds separately. So over here on this side, we're going to use our atomic numbers, again as before when we were looking at the RS notation, to determine which of these is higher priority. So over here we have a carbon, up here we also have a carbon. So those have the same atomic number, they're tied for priority, so we compare what's bonded to these carbons. Of course, our lower carbon would just have our hydrogens that we fill in up to make our 4 bonds, as always with our bond line structures. Up here we have our oxygen, and of course we would have 2 other hydrogens to fill up to our 4 bonds as well. Our top carbon has the bond to our higher priority oxygen compared to our lower carbon that just has the 3 hydrogens, and so we say that this group is our higher priority group. Now let's look over here on the other side of our alkene. So again we have 2 carbons, so they're both tied initially, and then we look at what's attached to each of those carbons. This one has another carbon attached, whereas this one only has 3 hydrogens. So again, we can say that this guy is higher priority. Now, both our higher priority groups are pointing to the same side of our alkene double bond, so we refer to this as our Z or cis diastereomer. Next, we'll take a closer look at the properties that our alkene functional groups share. Now, as we know, the properties of our molecules are strongly based on the electronegativity of the atoms involved in those functional groups. Over here in our alkene, so of course we have our 2 carbons with that double bond between them, and since they're both carbons, they of course both have the same electronegativity. So we have no dipole here between our 2 carbons, and of course when we don't have dipoles, that means that we can't have our stronger hydrogen bonding interactions or our strong dipole-dipole interactions. So we only have our weaker London dispersion forces, which of course then translates to lower melting points and boiling points, compared to things like alcohols, right? Alcohols, we can have hydrogen bonding, which then leads to higher melting points and boiling points. As we discussed before with alkanes, we can still have large melting points and boiling points for very large alkenes, but overall they'll have lower boiling points compared to alcohols of similar sizes. In terms of solubility, our alkenes are insoluble in water. Right, so again, like dissolves like, our alkenes only have those London dispersion forces. They don't form those strong interactions with our water molecules. And of course, we see this practically speaking as well. Right, so we have olive oil, of course, contains alkenes, and it doesn't mix well with water. Right, so if you've ever seen a salad dressing that separates out into an oil layer and a water layer, that's because it has a mixture of oils like olive oil as well as water-based solutions that aren't mixing very well together. Now, we'll end by looking at the reactivity of our alkenes. Now, of course, as we've seen, reactivity relates very closely with stability. So first, let's take a look at what factors influence the stability of our alkenes. And here we're going to, when we consider the stability of our alkenes, we encounter some similar factors to what we saw for carbocations. So if we take the structure of our alkene, so again, of course, we're going to have that pi bonding. So I'll go ahead and draw out butene. So we're going to have our two carbons at the center with those p orbitals that are overlapping side to side, as well as my sp2 orbitals that are overlapping head-on to make my sigma and pi bonds. And then we're going to have bond going out back at 120 degrees to get to, we'll put a hydrogen back here. And we have a bond coming out towards me. I'm shading that to indicate that's coming out towards me. And I'll have a carbon bonded over here. So I've got my carbon. This is going to be an sp3 hybridized carbon over here. On the other side, again, I'll have a bond going back, and I'll have a carbon attached over here. And a bond coming forward with a hydrogen attached over here. Okay, so the first thing you can notice here is this, of course, is a trans diastereomer of my butene, right? Because I have one bond going back to a carbon and another bond going forward to a carbon, right? So they're on different sides of my alkene double bond. Now, the next thing that I can notice here, so I've got my pi bonds here, my pi bond here formed from my p orbitals. And what we saw before with our carbocation is that we had this hyperconjugative effect from nearby carbons, where we had our sp3 orbitals that have a little lobe on the other end, and these can actually partially overlap with our p orbitals. They can get some side-to-side overlap similar to our pi bond, and they can help to stabilize our pi bond here. So they actually act very similarly to the sp3 orbital stabilizing the empty p orbital of the carbocation. In this case, we're stabilizing the filled p orbitals that are participating in this pi bond. Right? So I have my electrons represented by these little half arrows. These are pairing up in my p orbitals, but they can also overlap and kind of share some as well with nearby carbons. So again, this is another example of a hyperconjugative effect. If we add on additional carbons here, we're adding additional sp3 orbitals that can overlap with our p orbitals and can help to stabilize that pi bond. That increases the stability overall of our alkene. So as we add on more carbons, we're increasing the stability of our alkenes. So we can say that a more substituted alkene, so an alkene that has more carbons attached, will be more stable. So right here we have what we call a tri-substituted alkene with 3 carbons attached. We could add a 4th carbon up here to have a tetra-substituted alkene. or we could have a di-substitute alkene, or a monosubstitute alkene, or a unsubstituted alkene. So of course, tetrasubstituted would be more stable than tri, which would be more stable than di, mono, etc. And of course, this stability will also relate to our reactivity. Tetrasubstitute alkene is going to be the least reactive, the most stable, and unsubstitute alkene is going to be the most reactive. It's the least stable. Now, of course, as we saw before, we can have unique alkenes that still have the same substitution pattern. Right? So our two diastereomers here, our trans-butene and our cis-butene, are both di-substituted alkenes. So we might say that they're the same stability based on our substitution. However, we also have an additional factor to consider here, right? The effect of the trans versus cis diastereomer orientation. Now, in order to consider the effect of this orientation on our stability, we need to take a closer look at our structures. And of course, we want to think here about crowding of our molecule as well as this hyperconjugative effect. So when we compare our two diastereomers, so on this end we have our two carbons, which will each have their hydrogens. And we can draw in our carbons over here for our trans diastereomer. So we draw in those two carbons at the end. One thing that you should notice here is that our two carbons are much closer together over here on the cis diastereomer compared to my trans diastereomer. Right? So they're on opposite sides when we're looking at a trans diastereomer, whereas they're very close to each other here on the same side of our double bond in the cis diastereomer. So this is a crowding effect, or a steric effect. We refer to crowding as steric crowding. And we say that our cis is more crowded than our trans isomer is. So in terms of stability, trans will be always greater than cis. So first we can compare the substitution pattern of our alkenes to evaluate their stability. And then after that, if they have the same amount of substitution, so they're both di-substitute in this case, we can compare this crowding effect based on their trans or cis configuration. In general, the final thing that we can say about stability is that more compact alkenes tend to be more stable than more spread out alkenes. And this is the same effect that we saw for alkanes as well. Now, of course, while it's very important to consider the stability of our alkene in order to determine our reactivity, we also want to look at areas that might have high electron density or low electron density. Right? So we talked about nucleophiles and electrophiles when we looked at our alcohols and at the different nucleophilic substitution reactions that can occur with our different alcohols and alkyl halides. So with our alkene, we need to ask ourselves, is there any location where we have a higher electron density or a lower electron density? Now, as we saw earlier, we have no dipole in our carbon-carbon bond here, right? So that might suggest that we're relatively unreactive. However, we need to consider that our alkene, it has this double bond with our p orbitals with their 2 electrons and our sp2 orbitals with their 2 electrons. So even though we don't have a dipole that creates an uneven share of electrons on one of our carbons or the other, we do have a high density of electrons right here around our double bond. Right? So that double bond has 4 electrons crowded together in one space compared to our normal bonds that just have 2 electrons. So this does represent an area of high electron density. And of course, because of that, that makes it a reaction center, right? It's reactive because it has a lot of electrons that it can use to create a reaction. And so we can actually refer to our alkenes as being somewhat nucleophilic because they have all that electron density. Now again, they don't have a negative charge like we've seen in some of our nucleophiles. They don't even have a partial negative charge. But they do still have an area that has lots of electrons right around our double bond, and that can be used to create some reactions. Now when we look at biological molecules that have alkenes, such as our unsaturated fats, olive oil or those omega fatty acids, one of the things that makes these molecules unique is the presence of this reactive alkene double bond. That allows it to do some unique things in our body, but it can also cause problems for food manufacturers. So those reactions can lead to our food breaking down and can decrease the lifetime of our food. So this is why often processed foods will contain more saturated fats that don't have these alkene double bonds, because they then won't be as reactive. So our alkenes actually have a lot of reactivity compared to alkanes. Alkanes are relatively unreactive, whereas alkenes will play an important role in a large number of organic synthesis reactions.